All right, good Sunday morning. I'm going to quickly go through some review on gases in case you're interested in this for the test tomorrow. And the way I'm looking at it, the test will probably be about 12 questions or so. Should be able to be done in one period. Okay, so gases, just to make sure you remember, we were talking about pressure, gas laws, and then the ideal gas law. And you can look at this slide, just telling the properties of gases. We talked about that already: low density, compressible, and exert pressure. We went through the definition of pressure, force per unit area, and we learned that we could have different units: Pascal, torr, atmosphere, and pounds per square inch. And it's important to know that gases exert pressure in all directions. And again, that's about 14.7 pounds per square inch at atmospheric pressure. Well, here, what you're looking at is just a diagram saying that if we had some sort of arrangement where the pressure inside and outside of a can, for example, were the same, then we wouldn't have any effect on the can. But if the pressure was diminished on the inside of the can, people have a tendency to think that you're sucking out the air and then sucking in the sides of the can, but really it's a differential in pressure that's causing this can to collapse. The pressure on the outside, atmospheric pressure, again, 14.7 pounds per square inch, that's significant. So that's going to crush the can. Okay, let's get to the gas laws. Um, we will be talking about kinetic energy of gas molecules a little bit later. And if you remember that kinetic energy is equal to 1/2 mv squared, mass times velocity squared, where mass has to be in kilograms. And we can see there are different types of kinetic energy. We are only really talking about translational kinetic energy, which is the idea of a particle moving in straight lines. Rotational and vibrational are also modes of kinetic energy, and molecules can rotate. In fact, they do, and they vibrate. And that's very important to understand the vibrations of molecules for other reasons other than gases. We learned that we are looking at collisions with the walls that are totally elastic. And then we started getting into the gas laws. We saw Boyle's law. Volume was inversely proportional to pressure. So we were able to say V1 P1 equals V2 P2. So if you cut your volume down, your pressure goes up. And you saw that in lab, you saw that on questions in class, and it's a very easy concept to understand, I think. Excuse me, still waking up. Charles' law, relation between volume and temperature. We have direct proportionality. As temperature goes up, volume goes up. But never forget, you must use Kelvin. You must use Kelvin. If you use C, degree C on the problem, I'm going to mark the whole problem wrong. Okay, this just shows the linear correlation between volume and temperature. Notice as temperature increases, volume is a function of temperature. Linear function of temperature. And we don't need to look at that. We can combine gas laws so we can change more than one thing. And remember, I also showed you one where we can put the number of moles in the denominator as well. So P1V1 over N1T1 would equal P2V2 over N2T2. But either way, they're both called the combined gas law. And don't forget, when doing these, look out for rewards in a problem like if volume is held constant or if temperature is held constant. That means you can just eliminate them from the equation if they're the same on both sides. Here's a question looking at combined gas law. A cylinder of gas is kept at a constant volume as the temperature increases from 24.1 degrees C to 326.4 degrees C. Before you do anything, convert those to Kelvin by adding 273. So you can see this is a temperature and pressure deal here. Let me see, volume would cancel out, so it would be P1 over T1 is P2 over T2. So we get rid of those volumes, they're the same on both sides. And so we just go ahead and make sure they're just driving the point home here. You got to convert those temperatures. So my temperature goes up, or excuse me, my pressure goes up substantially from what it was. I'll skip through this. Okay, standard temperature and pressure. Do not forget this. 1 atmosphere, 0 degrees C. The volume of a gas at STP is 22.4 liters. I forget this here. You can look at this if you want to. How many molecules would be contained by the air in the room if it was at STP? Well, we can assume that the volume of the room is approximately 571.2 cubic meters. This is just an average room here. And that would be 571,200 liters. There are 1,000 liters in a cubic meter. So just going ahead here and converting 571,200 liters times 1 mole of gas per every 22.4 liters. And then we're going to say, okay, that'll give us moles. And then we multiply by Avogadro's number. And we have a huge number of molecules of gas in our room. I can just get rid of this one. We don't need to talk about that. And then there was the ideal gas equation. Now remember, we're not changing anything in the ideal gas equation. We're just looking for a missing variable. Lots of times we're looking for the number of moles so we can use it in a stoichiometry problem. You can pause this and try it if you'd like. Okay, we're doing an ideal gas. We're looking for moles. We've got temperature, volume, and pressure. So we rearrange that to solve for moles and plug and chug at this point, so we get 5.9 moles of helium. This is a good question. It says if all of the helium is used to fill 1.5 liter red balloons at 0.99 atmospheres and 32 degrees C, how many balloons will you end up with? Well, how might you approach this? We've got a temperature, we've got a pressure, and we've got a volume. Well, first of all, let's go back for a minute. We've got our moles of helium. And then we need to solve for the total volume of gas that we have. We've got 149 liters. Okay, well look, I have 1.5 liter red balloons. So how many am I going to be able to fill? Well, a little bit less than 100, right? Each balloon has 1.5 liters. You end up getting 99 red balloons. And if you happen to be a fan of 80s music, you would get the joke. Okay, this is a good one here. I would say try it. There will be one like this on your test, finding a molar mass of a gas. You can go ahead and pause the video and try this. All right, an unknown gas is collected in an 850 milliliter vessel at 1.02 atmospheres and 23 degrees C. The evacuated vessel has a mass of 138.45 grams before the gas was collected, and the vessel and gas have a combined mass of 140.12 grams. Find the molar mass of the gas. Well, if you know the number of grams of gas, and you know the number of moles divided by grams gives you the molar mass. And that's exactly what you need to do. You need to find number of moles, and then once you have that, we divide it by, you would subtract 140 minus 138.45, get the number of grams, and grams divided by moles is going to give you your molar mass. Okay, this was our density. Now remember I said density here sometimes was written as a letter that looks like a P, and it looks so much like a P that I just put D there for density, but that's a Greek letter called rho, R-H-O. And I would like you to look over a density type of a problem because there will be one on the test. Okay, an unknown gaseous hydrocarbon has a density of 3.24 grams per liter at 1 atmosphere and 28 degrees C. Find its molar mass. This is a plug and chug. Molar mass is equal to density over P times RT, and you get 80 grams per mole. Okay, gas stoichiometry. You should be able to do a gas stoichiometry problem. What volume of CO2 can be produced when 68 grams of methyl alcohol burns in air at 25 degrees C and 1.02 atmospheres. First things first, um, you need to figure out the moles of CO2 that are produced. Now, if you take a look, they're in a 2-to-2 ratio between methyl alcohol and carbon dioxide. So you can get number of moles of methyl alcohol, and then 2 moles to 2 moles, so you're going to get 2.1 moles of carbon dioxide. And now we have moles, we have temperature, and we have pressure. So we can use ideal gas law to get volume. And you get about 50 liters. So you see, these are not difficult. All right, I'll be following up with another video on other aspects of gases.